Hi, in this part of the vapor and combined power cycle, I'm going to talk about the actual Rankine cycle. The actual Rankine cycle can be the cycle which deviates from some idealized cycles. There are several kinds of irreversibility which can occur. For example, the piping losses, turbine losses, which occur when the turbine expands in a non-isentropic way. Irreversibility can also come from the pump when the pump operates in a non-isentropic ways. And the losses can be from the condenser where we have the cooling of the condensate to below the saturation temperature. All of these irreversibility will make the Rankine cycle to become actual Rankine cycle. Now let's have a look at a simple example to show you how to calculate the performance of an actual Rankine cycle. We will continue our work from the previous example, but in this case, pump and turbine are irreversible processes with pump efficiency of 85% and turbine efficiency at 87%. We want to determine the thermal efficiency of this actual cycle, and we also want to determine the net work output, net power output here. If the mass flow rate in the cycle is 15 kilogram per second, this is m dot. Okay. Now you can see that in this cycle we have two irreversible processes. The first one is the pump, the second one is the turbine. So it means that we have to recalculate the work required for the pump and the work that we would get from the irreversible turbine here. So we will consider first the pumping process. Pump from 1 to 2A. Okay. So from the given information here, we have efficiency of the pump at 85%. So neta of the pump equal to isentropic work divided by actual work. So that is 0.85. Okay, and isentropic work would be W1 2S divided by W1 2A, which is the actual work. Now from the previous example, we have already calculated isentropic work, and it is 6.05. We can then substitute the values and then calculate for the actual pumping work W1 2A, and that would be W1 2A equal to 7.11 kilojoule per kilogram. Okay, so this is W1 2A. Now we can move on to recalculate the work that we would get from the turbine, which is process 3. So we have turbine, which is process 4A here. From the efficiency of the turbine, you have efficiency of 87%, so it's 0.87. Okay, and for the turbine, efficiency would be equal to the actual work divided by the isentropic work. Actual work divided by isentropic work. So the actual work would be W34A divided by W34S, which is for isentropic work. And we already have W34S from the previous example. We can substitute the value, and that would be 1038.9. Okay, so in this case, W34A, or the actual turbine work, would be 903.84 kilojoule per kilogram. Okay, now having got the value of the actual work, we can use the energy balance in the process 34A to calculate the enthalpy at 4A. So we have we want to calculate H4A. Okay, from energy balance we have W34A equal to H3 minus H4A. So substitute all the value that we have. W34A, which is 903.84, equal to H3. H3 we already have from previous example, 3043.9 minus H4A. Okay, so here we have H4A equal to 2140.06 kilojoule per kilogram. Okay, now we can check the condition at point 4A, whether it is still in the two-phase region or it is now in the vapor region. So we have to compare the enthalpy value at this point with the enthalpy value of the sat liquid and the sat vapor. At 4A, the pressure will be 10 kilopascal. At 10 kilopascal, you get the enthalpy of sat liquid and sat vapor from the steam table. So you have HF at 191.81 kilojoule per kilogram, and you also have Hg equal to 2583.91 kilojoule per kilogram. Now you can see that when you compare the enthalpy at 4A with the HF and Hg at 10 kilopascal, you find out that your enthalpy lies between HF and Hg here. So it means that point 4A is located in the two-phase region. 4A is mixed phase. When 4A is in mixed phase, it means that the property at 4A will depend on the property of the vapor and the property of the liquid. Okay, but in this case, we don't need to calculate the fraction because it's not required by the problems. Okay, so we stop at this point. Okay, now we move on to recalculate the heat input to the process. The heat input to the process will be changed as well. Okay, so we will determine Q in. Okay, we will determine Q in, and Q in equal to H3 minus H2A. Okay, but at the moment we don't know H2A now, so we have to determine H2A first. Okay, find H2A. from the energy balance around the pump. Okay, we have W1 2A equal to H2A minus H1. W1 2A we have just received previously, 7.11 equal to H2A minus H1, 191.81. So H2A would be 198.92 kilojoule per kilogram. Okay, so you can now use H2A to calculate Q in. So you substitute H2A in the above equation. Q in equal to H3 minus H2A, and that would be 3043.9 minus 198.92, which is 2844.98 kilojoule per kilogram. Okay. You can now calculate the thermal efficiency of this cycle. The thermal efficiency of this cycle would be W turbine, which is 34A, minus W pump, which is 12A, divided by Q in, which is Q2A3. So you have all the values. You have 903.84 for the turbine work, minus 711 for the pumping work, divided by 2844.98 for Q in. So thermal efficiency of this actual cycle would be 0.315 or 31.5% efficiency. So this is the first answer. Now the second answer that we require would be the net work output if the mass flow rate is 15 kilogram per second. So W net will be equal to mass flow rate m dot multiplied by the turbine work W34A minus pumping work W1 2A. Okay. All right. Now you can substitute all the value. Mass flow rate 15 kilogram per second multiplied by 903.98 minus 7.11 kilojoule per kilogram, and that would be 13,451 kilowatt or 13.45 megawatt. So this is the network output when the mass flow rate is 15 kilogram per second. Okay, so you can see that this is how we do the calculation of the performance on the actual Rankine cycle when we have irreversibility in the pump and the turbine.